All right, this is the last part of the connective tissues notes. This is part 3, and I'm going to go over the specialized connective tissue types of fluid connective tissues and supportive connective tissues. So, the functions and anatomies of the ones we're going to go over are the fluid connective tissues, like I mentioned before, and supportive connective tissues, which primarily break down into the cartilage tissues as well as the bone tissues. And finally, at the end, I'll go over some pictures of all those tissues as they are found in a typical slide. So, fluid connective tissues are fluid. And the reason why they're fluid is mainly due to their matrix. So the ground substances that are generally either gel-like or firm, in this instance, contain only dissolved proteins and little to no insoluble fibers, which allows the consistency of the tissue to be fluid as a result, because there's nothing kind of holding the cells locked in place because the matrix is so soluble, basically. Generally speaking, you're going to see fluid connective tissues found in either blood, so blood is a fluid connective tissue, and lymph. Okay? So their matrix is the thick fluid that surrounds the cells. So blood has cells in it, but it's also a little bit sticky because the fluid around it is viscous. Viscous meaning a little bit thick, and that thickness is dissolved stuff. That's the dissolved stuff in this instance is actually the matrix of blood. Okay? So, when we talk about fluid connective tissues, the 3 main types of cell types we talk about are red blood cells, white blood cells, and platelets. So, red blood cells, also known as erythrocytes, look like this. They look like kind of donuts that are kind of like, not donuts, discs that have been pushed and dented in, or like frisbees that have been bent. Okay? And this red blood cells compose almost half the volume of blood that is found there, and they are made of cells, and their whole job is to transport the oxygen around the body. And in this instance, their red color, the hemoglobin protein inside of them that help them move oxygen around, is what gives blood its red color. The fluid matrix around them is actually clear. White blood cells aren't as abundant as the red blood cells. They actually only make a few % of the cells found in blood. But in this case here, they play a really important role in fighting off infection in your immune system, and they play a huge role in your immune system, and they kind of move throughout the blood and other fluid tissues like lymph, and they can even flow inside of your loose connective tissues to help seek out and look for viruses and bacteria that can cause harm to your body. Generally speaking, these cells, when stained, they're big and round and circular, and oftentimes they have like a really dark and sometimes horseshoe or weird shaped nuclei in the center. And that nuclei helps play a big role in its ability to look for and destroy dangerous organisms. Platelets, on the other hand, are tiny cell chunks that actually are useful, and they're found in your blood. And what they do is they kind of move around, and they got little spiky corners on them. And if you get a cut or anything like that, platelets are capable of plugging up that cut and preventing you from bleeding out. Now, fluid matrix depends on what it's made of. The most common fluid matrix that we discuss when we talk about fluid connective tissues is plasma. That's the fluid that surrounds the cells in your blood. Lymph is a different system. Lymph is a fluid that flows through what's called your lymphatic vessels. Your lymphatic system is kind of a weird system that flows side by side with your blood flow, except moves a lot slower, which gives more time for your white blood cells to travel around your body and look for viruses and other things. So, your lymph fluid is sort of like a parallel to your blood vessels. Think of your blood vessels as a high-speed freeway for moving stuff around your body, and your lymph vessels as like a slower side street that's moving stuff around your body. But in this case, it also has its own unique type of fluid and cells that are very similar to blood, but in this case, less red blood cells, a lot more white blood cells. But it's still kind of it's still liquid tissue flowing around your body. And finally, we have interstitial fluid. Interstitial fluid is fluid that's surrounding your cells, like all your organs are a little bit liquidy, and they eventually will diffuse and flow into either the lymph liquid or the blood liquid. They'll kind of pass and exchange fluid with them and go back and forth. All right? But ultimately, in blood and lymph, that's the source of their liquid that's surrounding their cells, the liquid matrix that's surrounding their cells. Most of the fluid that's not inside the cell can be found in your fluid connective tissue, especially blood. But again, the thing that's allowing them to be liquid is the fact that they have a lot less fibers than other connective tissues. So these are a scanning electron microscope picture of white blood cells, red blood cells, and platelets, for those of you wondering. So, in terms of a high school lab, generally speaking, you're not going to have images of other fluid tissue types other than blood. But the blood fluid tissue type is very distinct. So, this is the red blood cells, and then randomly, you're going to see white blood cells pop up. Those little specks that you see here and here, that's actually platelets. Platelets that you're seeing all around. That's a platelet too. Okay? So, that's what blood tissue looks like under a real microscope. All right, let's go over the last category of connective tissues called supporting connective tissue types. So these things help provide the scaffolding that forms your skeleton, that holds your organs in place and creates cages for your organs to hang off of or be protected by. And there's two main types of connective tissue, supporting connective tissue. It's cartilage and bone. So these connective tissue types provide a really strong and rigid framework that helps support your rest of your body. And the main thing here is they have lots and lots of fibers and deposition of lots of minerals, particularly insoluble calcium salts. They're going to help create that rigidity in your skeletal frame that helps you stay upright. All right, so the first type of supporting connective tissue is cartilage. Now, cartilage, unlike bone, isn't fully solid and full of calcium yet. It's generally speaking is a firm, solid gel, like a gel insole. It's not quite as hard as bone because it's like bone you can bend in any direction, generally speaking. Okay? Like you can feel it on the tip of your nose and in your ears. That's cartilage. All right? However, this is the only truly avascular connective tissue. So even dense regular tissue has some blood flow, but cartilage has none. And as a result, it really, really can't repair easily. If you chip your cartilage, generally speaking, it's not going to repair itself and you just need to get replaced cartilage, which you can actually get donated from a corpse. If you didn't know that, you can get donated cartilage to replace missing cartilage. But it's kind of hard to adhere, so most people don't have that. Now, in addition to that, the cells that do help at least maintain and keep your cartilage alive and supple are chondrocytes. So they don't necessarily help make new cartilage, but they do help keep and retain and make your cartilage or keep your cartilage healthy for the cartilage that you do have. So chondrocytes are cartilage cells and they're generally found in little pockets inside the solid cartilage matrix. And the pocket that they're sitting inside is also known as the lacunae. And the lacunae and the gel matrix is still able to pass material back and forth through diffusion with the outside fluid, but because it's not vascular, it doesn't have that active blood flow, throughout the cartilage tissue. It's getting enough stuff to live, but not enough to truly repair and grow quickly if needed. So imagine this is my cartilage background. The lacunae will be the little pocket that manages to form within the cartilage. And then the chondrocyte cell is going to be capable of growing inside the lacunae. That's what that means. So the lacunae is a little lake inside, a lagoon, what you might want to say, inside to create a pocket inside the solid backing. Now, how did this pocket even form in the first place? Well, actually, the way the pocket formed was because the cell itself existed first. And then what happened is it started laying down matrix around it. And growing matrix around it more and more, at least early on in its life. And then the matrix further away from it is a little bit tougher. And that's how it kind of forms a lake, because the cell is still sitting inside the pocket, but it's dumping matrix around itself that's firming up, and eventually all that's left is the little dent that the cell was sitting inside the whole time. And that's creating that lacunae. Okay? So, lacunae is that little pocket that you can kind of see. And the cell inside of that, which I'm going to color red, with its nuclei, is my chondrocyte. And this background over here is the matrix. Alright? And in terms of cartilage, you typically find them between your joints in your bones, especially there's a lot of cartilage there, and it's often kind of coating the end of the bones. Oh, by the way, for those of you wondering what this picture is, that's still the lacunae and the chondrocyte. And while blood vessels aren't inside the cartilage, there's some blood vessels kind of on the outside of the cartilage in other tissues, and those are capable of diffusing some material to the cell, though not a lot. Not as much as it should have. Alright, finally let's go over the types of cartilage. So there's three main types of cartilage: elastic, fibrocartilage, and hyaline cartilage. So elastic cartilage is a cartilage that has extra elastic fibers in it to give it a lot of bounce. Mainly, you're going to see it in your ears. That's the big location. So you can feel the edges of your ear and just bend it forward, and you can let it go, and it'll just bounce and flip right back. And it's very soft and malleable, but you can still feel that little bit of firmness. That's elastic cartilage. All right? So in this case, there's a lot of the elastic fibers, but there's still decent amounts of chondrocytes in the lacunae, which is going to kind of create kind of a bug eyeball looking thing. So, in terms of the images under a microscope, you're going to see these big cell eyeballs in a microscope with like clear thin fibers running throughout. All right, fibrocartilage, on the other hand, fibro is fiber, like a fibroblast. So in this case, this is a cartilage with lots and lots of fibers. It actually kind of looks like dense regular tissue, a little bit more spaced out, but with eyeballs in it, or the chondrocytes. So, and you typically find fibrocartilage in the cushions between, as cushion disc, vertebral disc in your spine. So your vertebrae holds a lot of your weight up, or your spine, for those of you who don't know that vertebrae is spine. And in between, because there's so much weight on it, you need a lot of cushioning between the spine bones so they don't crush each other. And that cushioning is made of fibrocartilage, which makes it extra firm but still bouncy. So it's going to give you that protection, but without wearing away very easily and very quickly. It's going to still get thinner with time, but it keeps its shape admirably for a really long time. Like I said, it's got a lot of the fibers almost like, in the one direction, almost like dense regular, but you're gonna see a lot of those like eyeball, lacunae, chondrocyte combinations throughout. And finally, we have hyaline cartilage. Hyaline cartilage is, for whatever reason, their lacunae look like bug eyes because they're different chondrocytes. There's more than one chondrocytes in each pocket. So, in addition to that, for whatever reason, the hyaline cartilage, there is some fiber in there, but they're not visible under a microscope, so you don't see a lot of fibers in the microscope itself. And as a result, it's mainly you see the gel ground substance, and it creates this kind of glossy, glassy, iridescent finish in the microscope that's really pretty, and that's of multiple colors, but it's very smooth looking, and it's very abundant in the body. You see it in your ears, in addition to the elastic cartilage. It's on the part of your ear that's more towards the inside, that's a lot more firm. You also find it on your nose, which is like flexible but not as bouncy as your outer ear, as well as the end of bones and in your ribs as well. All right, so let's look at some images of them so you can kind of see it. So this is hyaline cartilage, so you can kind of see that glossy background doesn't have a lot of fibers, and it's got a lot of eyeballs in it. Over here, you can see it looks kind of like those fibers are running parallel. There's a little bit more spacing, but it looks really similar to dense regular tissue. And then over here, this is actually what elastic tissue looks like. So it looks kind of like dark spider webs almost, not like cracked glass, but dark spider webbing kind of in between and around the lacunae eyeballs. Finally, last tissue we're going to go over is called bone tissue, also known as osseous tissue. All right, so bone connective tissue, also known as osseous, is a tissue, connective tissue but in this case, its matrix has hard calcium compounds that create this rigid, tough structure. But it still has a little bit of flexibility in it due to the collagen fibers. That's why our bones don't crack when we jump up and down. But if you know, a dead skeleton is actually really fragile because all the cells that make the fibers have long died, so it no longer has the fibers to keep it flexible and together, and rather it's just calcium at that point, chalk, and it can crush really easily. But that addition of collagen is what allows it to be strong and resist shattering. That mix of collagen with the calcium chalk type substance. All right, so the main cell that helps create those fibers, as well as help maintain the matrix and help produce the calcium and keep it in the right amounts, is the osteocytes. So they're the cells that help form the bony calcium matrix and maintain them. And again, they're going to sit inside the lacunae for the exact same reason, where as it was laying out the solid matrix around that cell, it kind of locked itself in place, and then it was stuck in a pocket due to the bone house that it built around itself. So the lacunae is also found in this instance. Now, the structure of bone actually ends up looking like rings. This is kind of an ugly picture, so I'm going to try drawing a slightly better picture of a bone. So, bones it's kind of a weird shape, but basically what happens is they have little pockets forming around a circle, and the inside of the bone circle actually is a tunnel that allows blood flow, so there's lots of food around it. So the cells that are growing bone really want to be as close as possible to the center of the blood flow, but they're still laying around a lot of matrix around the outside. So inside each of these pockets is our lacunae, or is a lacunae, that it's a pocket is a lacunae, but inside each of those is a osteocyte that's laying down matrix. And that's kind of forming the outer edges. And around that is more osteocytes that are trying to grow. but there's no more space around the campfire for the blood vessels, so then they end up kind of growing on the outer edge of that. And then that's what creates those rings that you see that eventually form the bone. And then eventually, there's a limit to how large it can get. So eventually, that's the end of the bone, and there'll be a different bone clump of osteocytes next to it. Okay, so then there'll be side-by-side bone cell chunks with the osteocytes and the lacunae side-by-side in your bones. So this is a picture of bone tissue, so you can see the rings. So it grows like rings on a tree. So they get as close as they can to the blood vessel, and then when they run out of space, they grow another ring but there's a limit to how many rings they can grow. And then but each of these blood vessel tunnels provides another resource for bone cells to grow around them in circles. All right, that concludes most of the notes. Last thing I'm going to do before I go over the takeaways is just give you some more histological examples of cartilage tissues, okay? So let's go over, remember, there's 3 types of cartilage tissues: elastic fibrocartilage and hyaline. So let's just look at real examples of that so you get a good idea of what they look like, and then we'll go into the takeaways. All right, so this is another way that you can stain elastic cartilage. Kind of ugly. The staining I'm not a huge fan of, but you still see those eyeball lacunae and this kind of spider web around everything. That's how you know it's elastic cartilage. Here's another example of that elastic cartilage look. Fibrocartilage, just reminding you, it's got the ripples of dense elastic tissue with random eyeballs, or the chondrocytes and lacunae. So this is kind of a picture of that. So you see the ripples of dense fibers, but you still see random lacunae throughout. This isn't the best picture of it though, but that's sort of the idea. And finally, hyaline cartilage can look like this to an extent. It's got all those like many merged chondrocytes all together, creating that kind of multiple eyeball effect. So here's another example of hyaline cartilage and that kind of glossy, iridescent finish. All right, takeaways. Fluid connective tissues, as a recap, contains cells and is characterized because of that liquid matrix around those cells, which have much less fiber than other connective tissue types, which also, because it's fluid, allows it to transport a lot of substances inside that matrix. The solid and flexible cartilage is useful for providing soft, elastic protection and connection between body parts. And especially supportive cartilage, though, things that you need to provide extra support from force, needs extra fibers to help maintain strength so that it can hold its shape and not get damaged right away. And finally, bone, more than anything else, has a really firm matrix due to the calcium, though it still has a little bit of flexibility from the collagen, which is going to allow it to have that really firm rigidness, but not be brittle enough to break. All right, that concludes notes for the connective tissue section. Move on to any other work you have for the day. Bye.